expressions. And so the first story problem is this idea of deer and predators. And we've got this capture and release project that has determined the number of deer per square mile is expressed by the D of P equals 75 over P, where P is number of predators and D is the number of deer. As the number of predators decrease, so as our predators decrease, what is going to happen to our deer population? So as we have less people eating deer, more deer survive. Yay. Oh, oops. The question actually asks if predators increase, though. So if we had it the other way around, the more predators we have, the more deer that are getting eaten, so the less deer we've got. Okay, so we got that reverse piece going on. Okay, evaluate these functions. So at D of 1, if there is only one predator in the area, how many deer would we expect to have? We've got 75 over 1, which would be 75. If I've got 3 predators, so D of 3, how many would we expect? 25. And lastly, if we've got 5 predators, D of 3 or D of 5, we'd expect to have 75 over 5, so 15. Good. Okay. What happens to the deer population is the number of predators becomes very large. So we have lots and lots and lots of them. What's going to happen? They go extinct, right? Or mathematically, we could say they get eaten. Right, that's a good mathematical term of what happened. Okay, lots and lots of predators are deer, they're gone. Okay, they're approaching 0. So last piece, graphing this function with an appropriate scale, and then describe what happens as our predators get very, very small. So if we think about what this looks like, again, we have our generic 1 over x approach to it. So in that first quadrant, which is realistically all we're looking at, this is what would happen. As we're approaching 0 predators, we see that our population continues to increase. So if there are no predators, nothing's killing off the deer, it's going to continue to grow and grow and grow and grow exponentially. Right? Similar to humans, the better medicine we get, the less things that are killing us off, so the more of us there are. We live longer, we continue to breed more, there's lots and lots of people. Yep.
So as predators, either Y or X.
So in this case, our number of predators is written as predators is our X. So this would be our number of predators, this would be our number of deer. So as predators approaches 0, our deer heads off towards the infinities. Okay. All right. So the first couple of questions will be similar to those. We'll be trying to identify how things behave in a rational sense. All right, today's stuff has been complained about all day, so you may have already heard about it. Okay. So it's not super complex, but it's a little bit confusing. Okay, so we're going to go from thinking about a single equation into one equation being multiple equations. So in this case, I'm going to say that this is the behavior of my graph, negative 1.5 times the absolute value of x minus 5 plus 10. So this piece of my graph, and I need to know when it behaves like that. Okay? And then it's going to behave like this in another spot. Okay? And you're going to have to take this and write it into a single piecewise function. Okay? So a single piecewise function, or f of x, is going to equal now a set of equations. Okay? So there's multiple of them. In this case, 2. The first equation is this negative 1.5 times the absolute value of x minus 5 plus 10. Okay? That's our first equation. In the book, it'll just show a gap. Otherwise, sometimes you'll see them put like a semicolon or something to show that, hey, that's my function. Now we're going to talk about the domain. So the first piece is the function and how it actually behaves. The second piece is going to be the domain piece of it. So where does it behave like this? And so in this case, the first one behaves like it from 1, including 1, because of the closed circle, all the way up to 7, excluding 7 because of the open circle. So 1, our x will be greater than or equal to 1, but less than 7. That's how we would describe that behavior for that specific domain. Now I only have a chunk of that, or a piece of that function. Then it's going to behave like the second function. During the given domain from 7, including 7, all the way off for forever. So for all of our x's that are greater than or equal to 7, we will behave like this. Okay, so we're going to have the behavior of the function and then where it behaves like that. So that's kind of the general concept of today. You're going to have pieces that are put together into a single function so we can have it break up into multiple pieces. The next one, which I thought was going to be one of the easier pieces, but seems to be the most confusing at the moment, is you're going to evaluate these piecewise functions. And so it's going to, this one question is actually asking you 1, 2, 3, 4, 5, 6 questions. You're evaluating it at these pieces. So you've got these 3 pieces in one piecewise function. And then you're going to evaluate it from here. What you're looking for is, h of negative 3 is asking what? X is negative 3. Good. So I want to figure out negative 3, does it apply to all 3 of these or just one spot? Just one of them. And which one of them? See?
Why is there such a big gap between the 5 and the...
So this is, like I said, I put semicolons in here to split it up between functions and the domains. They will just put big gaps. If it makes more sense to you, go ahead and put like a semicolon. So the first part of this is the function. The second part is the domain. So if I'm looking for h of negative 3, negative 3 fits into which one of these domains? The top one, because it's less than 0. So I only need to evaluate h of 3 in that function. So h of 3 will equal 2 times negative 3 plus 3. Or negative 6 plus 3, which is negative 3. Okay? So then if we looked at something else like h of 1. h of 1 would fit into which domain? First, second, or third one? Second one this time. Okay? So we're going to evaluate this as 1 squared plus 1, which is 2, or 1 plus 1, which is 2. So h of 1 is 2. Then there's a weird one. So they're going to ask for h of 2. Which domain does h of 2 fit into? Second one says x is less than 2. Does that include 2? No. Okay. Third one. Third one says x is greater than 2. Does that include 2? No. So what is h of 2? It's undefined, right? There is no defined function for that domain of 2. Yes, April?
So, like, the third equation is just 5.
Correct. So let's check that out. Let's look at h of 3. Good. It's just 5. Okay? So when I have h of 5, or sorry, h of 3, which domain does that fit into? The third one, because it's greater than 2. So this is y equals 5. So if I plug in 3 for x, is there an x? No, so it doesn't matter what x is, y is always 5. Okay? And so if we thought about this graphically, and I'll show you how to graph these in a bit, okay, we can see why this works out. You've got 2x plus 3 for all the stuff down here. So we've got some line, and that's forever. Does not include, so that's an open circle. We've got x squared plus 1, so it behaves like a parabola in this spot. Open circle doesn't include there. And then at 5, open circle, or at 2, it behaves like just equals 5. So it's just that horizontal line. So at x equals 2, we have that undefined moment. And then anything beyond 2, it's just 5, doesn't matter. It's just always 5. So that's kind of what that would end up looking like. So the next piece we get to work on is, let's actually graph these. Cool. So we'll get to graph these, and then we'll get to take the graph and write the equation, all sorts of fun stuff. So they will ask you to graph them on your graphing calculator. If you want to, go ahead and do that. I'm not going to slow down and teach you exactly how to do that. If you want to, it's on page 166. Page 166 will show you the detailed descriptions on how to do it on your calculator. Essentially what you do is when you go to your y equals, you type in the equation, and then you have a division bar, and inside parentheses, you give the constraint. So you would say x is greater than 2, or x is less than negative something. If it's between a range, you have to say x is greater than 5 and x is less than 2, or whatever it is. So you got to give that didn't make sense. Greater than 5 and less than 7. Okay? So you got to actually give those. In order to type in those words or use the inequalities, you want to go to the test, which is second math. Okay? But again, inside the textbook, it'll show you details on how to do that. Otherwise, most of these, they're all just basic horizontal and vertical shifts, so we can do these by hand. And so we'll just do these by hand if you don't want to do them on your calculator. Number 13 would look like this then. From -6, and I'll show you 2 different ways to do this. There's multiple approaches. Whichever one makes most sense to you, go ahead and use. At -6 to 2, I know I'm going to behave like this function. Okay? That's a linear function. So I'm going to grab my 2 endpoints and just connect them. So when x is -6, -6 plus 2 is -4. So I'm going to get this coordinate point with an equality, closed circle. So this is -6, -4. I'm going to grab my other endpoint, which is 2. 2 plus 2 is +4. So I'm at the point here, 2, 4. I know that's a straight line, so I'm going to connect the dots. Okay, my y-intercept is 2. I have a slope of 1. That makes sense. Hopefully everything's working so far. Okay. Second piece, I'm going to see that I have greater than 2, and it's going to behave like an absolute value that's been shifted to the right 4 units. So we're going to go over to 4. Okay, so there's 4 units. And then I'm going to test my endpoint. So at 2, 2 minus 4, take the absolute value of that, which is +2. 2 times 2 is 4. So yes, we share this point. And then we're going to see this thing inside the graphs where one of them is an equality, so it has the closed circle. One of them is not, so it's open. If it's the exact same point, I'll enlarge this. What you're going to see is a closed circle for the first equation and an open circle for the second equation. So it looks like it caps over the top of the closed circle. So that's one of those kind of weird things. When you share an open and a closed circle, you'll have a cap over it. In this case, it's an absolute value. So we've got our V shape, and then there is our graph. Okay, so now we've put together a piecewise function graphically. The other way to take a look at it, we'll show it as a demonstration on another problem, is you can actually just plot the entire graphs and then erase the parts that aren't important. So the parts that are included in your domain. So let's take a look at number 15. So number 15, if we were to sketch this, I know I have the function negative x minus 1 squared plus 5. So it's a parabola that shifted right 1, up 5. So at the top of my parabola, I have an upside down parabola because it was a negative. I have a line 2x minus 12, so negative 12 is my intercept. So it continues forever. Okay? So I have these overlapping functions right now, and you're like, oh my gosh, there's too much stuff going on. That doesn't make sense. Now we can go back and figure out what parts are important. Right? So this is from negative 2 to positive 4. So at negative 2, we end up with 9, negative 9, plus 5 is negative 4. So I end up with an endpoint here. That's at negative 2, negative 4. After we evaluate that. Anything beyond that doesn't matter to us, so you can erase it. There we go. And then my other endpoint was at positive 4, so 4 minus 1 squared, negative 9 plus 5. So again, this will be at positive 4, negative 4. My sketch isn't super to scale here, but we can live with it. Okay. Everything beyond that isn't super important, so we can erase it. And then our endpoint here, plug in 4, 8 minus 12, we're at the exact same point, but we're going to have the end cap, and then it's everything positive, so we can erase all the stuff that's behind it. Okay? And then we end up with what is left for our piecewise function. So if you want, go ahead and just graph the stuff that's in the domains, or if it makes more sense to you, graph both equations, and then erase the stuff that's not in your domain. Okay. So a couple different approaches. And I'm sure there's more approaches as well. All right, next thing we're going to take a look at is filling holes. Okay, so a continuous function means what? You remember what a continuous function is? For example, is this a continuous function? Why not? Oh, let me put arrows on both ends. Is that a continuous function? Okay. Is this a continuous function? Why is that not a continuous function? Because it's separated. Okay? Our basic definition is a continuous function is something you can build without lifting your pencil off the paper. So as weird as it may look, as long as you can do it in a single pen movement, that's a continuous function. Right? There's no holes, there's no gaps, we're not jumping, and we're in good shape. What we're going to see here is we're going to have holes that get created when we graph these. Okay. So let's take a look at 23. 23 can be factored on top into an x minus 3, x plus 3. That over x plus 3. What happens to our x plus 3s? They cancel out. Good. What do you think that graph is going to look like? I had a parabola over a straight line. The straight line's canceled. What do you think it's going to look like? What's left? What straight line is it, Bree? What specific straight line is left? Good. X minus 3. That's what's left, right? So everything that was x plus 3 that made that into a parabola got canceled. So this leaves us with just the straight line x minus 3. So it's going to behave like that line. Now there's one catch to this. What point doesn't exist on that line now? Negative 3. Why doesn't negative 3 exist? Good, because from the original equation, if I plugged in -3, the whole thing freaks out, right? So I don't have a point there. I've got a hole. How do I plug that hole? Duct tape? Good guess. What kind of specific duct tape do we want to use? Where are you going to put your duct tape? In the hole. How do I find the hole, though? What's my x value going to be? -3, right? That's what we found. Where am I going to plug in -3 for x? For the x minus 3, because that's what my line is. So if I plug it in for that equation, I see that I need to plug it in at y equals -6. So C needs to be -6 when x is -3 in order to plug this hole. Does that kind of make sense? Okay, so what you're going to end up with is equations that have a piece that cancels out, and then you're going to have a hole that's left over. We can probably leave that down so you guys can still see, right? I think he meant well by doing that. All right, so you'll end up getting a hole, and then you got to go take the x value, plug it into whatever's remaining, because that's how the rest of the function behaves. Figure out its output, and then you can plug the hole with it. All right, we'll take a look at one more thing here today before tomorrow. The last piece is I will give you a graph and ask you to give me the equations. So again, all we're looking at is multiple equations. So if we want to take a look at 27, I can find the equation of each of these lines, and then I can piece them together. So this first line has a y-intercept of -1. Okay. It has a slope of up 1/2, so 1/2. So 1/2 x minus 1 represents that line. Where does it behave like that? It goes from -4 to +2, but not including +2. So our x is greater than or equal to -4. And again, I'm going to put these semicolons in there so you see the separation between the function and the domain. And then it's going to be less than 2. Right, so there's our domain that it behaves like that. The second piece of this function then has a slope of 3, up 3/1. So 3x. My y-intercept, you can either solve for it algebraically, or on the graph we can go down 3/1, down 3/1, which will get you to -6. And it behaves like this for every value greater than or equal to 2. There are my two pieces with their domains. I can now take them as f of x equals, and I piece them together, and now I have a piecewise function. Okay?